So welcome everyone. Thank you for joining us for the DeFord Lecture Series. My name's Elizabeth Catlos and I'm a faculty member in the Department of Geological Sciences at the University of Texas at Austin. We're part of the Jackson School of Geosciences, and the DeFord Lecture Series is our departmental seminar series. It's been a requirement and a tradition for all graduate students since the late 1940s. The lecture series is named after Professor Ronald DeFord, who joined the university as a professor in 1948 with the purpose of enhancing the quality of the graduate program of the department. Our speaker today will be introduced formally by Dr. David Morig, who is the Peter T. Flahn Centennial Chair in Geology and the Associate Dean for Research in the Jackson School of Geosciences.
Okay, well, thank you, Dr. Catlos, and good afternoon, everyone. It is my great pleasure to introduce Dr. Deon Knights, who is a recent graduate of The Ohio State University and currently is an NSF ERA postdoctoral fellow at West Virginia University in the Department of Geology and Geography. Before completing his PhD at The Ohio State University, he also took a master's at that same institution and then was an undergrad at the mighty University of Delaware. Deon's advisor at The Ohio State University was Audrey Sawyer, who was a graduate of our school, so some of you may know her. And today, Deon is going to talk to us about his studies looking at the fate of nutrients in coastal freshwater systems. And he will do that by bringing in some coastal ecohydrology, probably some river groundwater interactions, and the mysterious new term that I learned today, riverine nutrient cycling, spiraling, it's spiraling. So with that, I will turn over the floor to Dr. Knights, and thank you for sharing your work with us.
Okay, thank you very much for the lovely introduction. It is a pleasure to be here, and I look forward to giving this talk. I'm going to assume that you guys can see my screen and can hear me, and if that's not the case, I'm sure somebody would alert me. So I'll be talking about the coastal freshwater systems, and I'll discuss some work I did in Wax Lake Delta and the Great Lakes. And just some background to get us going, why I'm interested in this topic. Human beings are really good at adding a bunch of nutrients into the environment through things such as the burning of fossil fuels or some agricultural practices. And some nutrients infiltrate the soil and are transported to the coast through groundwater aquifers. And some nutrients are intercepted by surface water and transported that way. In fact, fluvial processes are responsible for transporting a massive amount of nutrients to the coast, and some estimates indicate that up to 1.6 million tons of nitrogen is transported to the Gulf of Mexico through the Mississippi River annually. Nutrients at the coast can have negative environmental consequences. For example, excess nutrients can lead to the development of harmful algal blooms, as can be seen here. And harmful algal blooms are dangerous to people and aquatic organisms. And they can be very expansive. Sometimes they're present in all of the Great Lakes, and you can see here in Lake Erie, at times it covers almost all of Lake Erie. But the transport of nutrients to the coast is highly straightforward. In groundwater, you can have absorption of nutrients, for example, phosphate onto clay minerals, and it can be removed from the water column that way. In surface water, you could get nitrate being transformed into nitrogen gas through a process called denitrification, and it could be removed out of the water that way. And some hydrologic systems are especially complicated, and we do not have an accurate understanding of nutrient transport within them, such as coastal aquifers, where you have direct groundwater discharging water offshore below the sea level. So it's essentially invisible, very difficult to gauge, and it's very diffuse, so it's not a point source. So difficult to monitor, and you can have deltas where you have this distributary network, which makes monitoring the water flow very difficult, and that's the thing nothing about the nutrient flux within the water. So this brings me back to my research interest, which is understanding nutrient transport and processing in these very complicated but under-monitored coastal systems. And today I'm focusing on two types. I'll spend the majority of my time talking about river-dominated deltas. And then with the few minutes that we have after that, I'll talk about some work that I did on shallow coastal aquifers of the Great Lakes. So what I'll do is we'll go through the key points up front, and then we'll go through the methods and the results together and come back at the key points. So for the river-dominated delta part, I'm going to show that higher elevation wetlands contribute most to nitrate removal. High-sitting deltas are more efficient at nitrate removal than lower profile deltas. And then we'll see that nitrate retention is likely limited to only a few percent, so less than 7%. And my research question for that is how are nitrate removal rates spatially distributed across ecologic zones on Wax Lake Delta? So to answer that question, I focus on Wax Lake Delta, and it is located just west of the Atchafalaya Delta in southern Louisiana on the Gulf Coast. And the Wax Lake Delta, as with many deltas, are made up of distributary channel networks that have very complicated flow regimes. Conceptually, you can have flow within the main channels. You can have overtopping of levees. You can have flow within secondary channels. You can have bidirectional flow within the island embayments, and you can have bidirectional flow within secondary channels. So very complicated flow regimes. And you can have very different vegetation communities. And I'm showing you pictures of the same delta, and you can see in one location, you could have these large woody trees, and in other locations, you could have all these floating vegetation types. And these form very different ecogeomorphic zones. So the goal, again, is to understand how reactivity on Wax Lake Delta varies across these zones. And what would be nice is I would hope to predict removal based off of things we can easily measure, because I'll show you in a second that actually getting this removal rate is a challenging process. So if we could, relate removal to things such as, greenness, water depth, even elevation or sediment properties, we could use this to say something about removal in other deltas, hopefully, without having to go out into the field. So I did this using a benthic chamber experiment, as can be seen here. So a benthic, an open atmospheric benthic chamber, that is a very big fancy word for it. Simply a 55-gallon drum with the tops and the bottoms removed. So we essentially stick this drum into the sediment about 15 centimeters or so below the sediment water interface. And we stand there on the delta, in the water, in the heat, sampling the water that is trapped in the mesocosm and trying to avoid alligators and snakes and all of that fun stuff. So very challenging work. I'm going to pause right here and say that I'm going to talk about nitrate removal for this entire presentation. And we know that there are different processes that could remove nitrate from a system, such as denitrification, which I mentioned earlier. But you could also get nitrate being taken up, assimilated into organic nitrogen in plant matter, or you could have dissimilatory nitrate reduction to ammonia. These are temporary and permanent different sources of nitrate removal. But for the purposes of this experiment, I'm lumping all of those processes together, and I'm calling that nitrate removal. And we're not interested yet in the different removal pathways. So again, we have our benthic chamber experiment. So we deployed this on 5 main sites on this island, Mike Island of Wax Lake Delta. Within these sites, we have about 6 benthic chambers or so, and we target the different ecogeomorphic zones. We have the upper zone, which we did not sample because it is generally sub-aerial, and we need standing water to use this approach. But that is mostly on the island levees and the northern extremes of the Delta Islands. But what we did sample, and you can see what our chamber scheme looked like here, were the intermediate zones that's flooded. And then if you go a little bit down in elevation, you tend to get more open water. Still some vegetation. This is the lower zone here. So what I'm showing you here is one example from the intermediate zone and one example from the lower zone. What is important, I'm just trying to show you what the data looks like when we sample the water from the mesocosm over time. We have our nitrate concentration decrease if we are relative to some conservative trace chloride here. And if we take the natural log, the slope of the natural log of this line, this removal, we are able to get a first order uptake rate constant. And if we multiply by the depth of water, we're able to get a VF, or mass transfer velocity. So that's our nitrate removal. And that has interesting units, interesting velocity units. And you could think about that as like the rate at which nitrate is sucked out of the water column. So this VF is going to be our nitrate removal parameter or variable. Before we move on, we wanted to make sure that what we are measuring within the mesocosms are representative of what is outside. So we just, I'm showing you examples, again, one from the intermediate, one from the lower zone. There's many more of these, but if you look at the pH, the temperature, what we're trying to see is that the chamber chemistry and the surface water chemistry trends similarly, and we do see that. So we're comfortable that there won't any bottle effects, that the mesocosms were representative of the actual delta. And we also measured a bunch of different things. Well, we use NDVI. We measure nitrate concentration, the grain size, bed elevation, water depth, and sediment loss on ignition to see if we could come up with some sort of relationship between what removal and these parameters. And what we found was a nice little regression equation here. A VF is dependent on NDVI as well as nitrate concentration. And we have an R-squared here of 0.721. This is what our model results versus our observed results look like. And this is great news. This is saying that this VF depends on NDVI, which is a remotely sensed metric. So now we can, upscale this finding to, most of acidic delta, and hopefully you can apply it to other similar types of delta you control for, similar climates and flow regimes and whatnot. This is great news. So now we have the tools to answer research question number one. And when we upscale our findings based off of NDVI, I'm showing you the potential removal. So that is this VF here, and this velocity units. The gray represents the subaerial upper elevation ecogeomorphic zones that we're not really capturing. But what we're seeing here is we get a lot of removal potential. So the potential for nitrate to be removed in the northern parts of the delta islands, and we have low removal in the channels and in the lower parts of the embayment here. And we could break this down by ecogeomorphic zone. So we have the intermediate zone, we've seen about 2 to 3% removal. And the lower zone is about 1 to 1.3% removal. But what is interesting is the intermediate zone makes up about half the size of the lower zone, yet it contributes about twice the amount of removal. So it's very interesting. And another way we could do a similar sort of experiment using our field observations is we can break up the delta into a series of links and nodes. So I'm showing you here just the channel network. We have discharge is being partitioned downstream. The darker colors represent greater discharge, the lighter colors represent less discharge. And just for right now, I guess the most important thing to know is, here we have the main channels with the greatest discharge, and we capture some secondary channels over here, and we can see there's not that much discharge. So keep that in mind a little bit later. And then we come to the more or less the nutrient spiraling part of this, where you essentially where we're able to predict the concentration downstream from each link, and that is based off the concentration upstream. It's also based off of this nitrate removal rate and some hydraulic load. And this sort of calculation considers the physical transport processing as well as the reactions. And if you do this experiment, we're able to color code the delta by the efficiency. So we could say things like, how efficient is each link at removing nitrate? So if you look at this little simplified delta right here, this little schematic, I have a delta with 3 links, and I'm highlighting one link of interest. We're looking at the concentration upstream minus the concentration downstream divided by what came in. So what we are seeing here is that some of these secondary channels are pretty efficient at removing nitrate. Another way to look at it, though, is how much does each link contribute to total nitrate removal in the delta? So again, back to this little schematic here of our 3-link delta, we have the concentration upstream minus the concentration downstream, but instead we're dividing by what came in at the inlet. And what we're seeing is some of these major channels here are popping out as more important for removing nitrate within the entire delta. So to summarize these two graphs, what we're seeing on the left is that the secondary channels are very efficient at removing the nitrate they receive. However, they don't really receive that much nitrate to begin with because it doesn't receive that much flux. And some of the bigger channels, although they may not be as efficient, they are contributing more to nitrate removal because they receive so much more nitrate. And we could summarize these two findings by saying hotspots are intermediate elevation areas. We saw that along the eastern branches because they likely receive more nitrate and have higher demand. So next I'll show you some additional models that will help us transition to research question 2. And for this, I work with some collaborators. And here we have a snapshot of Wax Lake Delta. This is a fully calibrated hydrodynamic model of Wax Lake Delta. I'm showing you a snapshot at low tide and high tide. Here we have flow within the inlet. We have some no flow boundaries represented in red, and flow is allowed to escape downwards and outwards at low tide. In fact, it does do that. At high tide, we get some flow reversal, so we get water coming into the model and flooding the some of those islands here. So with this hydrodynamic framework, I was able to apply a reactive transport model in Delft 3D on top of it. And now I'm able to say something about reactions. So here we see nitrate coming in with just a little bit over 1 milligram of nitrate per nitrogen per liter. And what we see here is that nitrate concentration stays high in the channels. It's that deep red color. But we do see some removal on the islands, very similar to our potential removal rates that we saw earlier on. But what I think is very interesting here is we see here a lot of battle between transport and processing. So at low tide, on the islands, you get a lot of processing, you get a lot of removal. If you take a look at my island here, for example. But at high tide, when you get that flow reversal, you get flooding of the islands with water that is high in nitrate concentration. And that processing is not able to keep up with that pulse of water that is coming in at high tide. And then at low tide, you get that draining again. So if this was a video, we'll see sort of that flushing and draining of nitrate as processing is able to keep up, and then flooding takes over at high tide. When you calculate the total amount of nitrate that is removed due to processing, we see only about 5.2% of removal. So if we take a look at our 5 field sites on Wax Lake Delta, on Mike Island, I'm showing you the depth here. So you can see that high and low tide with time during our 5 or 6 day period or so that we were out on the delta at our 5 different study sites. Down here, we have the results from the reactive transport model. So you're looking at nitrate concentration on the y-axis again with time, and our model results are the solid line, our field observations are the hollow circles. And what we see here is that at site 4, site 2, and site 5, we get that high nitrate concentration. The model kind of predicts that, similar to what we observed. Right here at site 2, right about when we would have started to see that decrease in nitrate concentration as reaction keeps up, we actually had to abandon that field day and leave due to a storm that was fast approaching. So we grabbed our Benthic chambers and headed out of there. But at site 3, we are seeing, the model and the observed values are seeing that removal in nitrate with that decrease in tide. And at site 1, we did not capture a pulse in nitrate concentration. We didn't capture that flooding response, and that's probably due to us being in a little bit of a local depression that may not have been as hydrologically connected to the major delta per se. But what is important with site number 1 is it's the only site that we found 0 or near 0 below detection limit nitrate concentration. And the model also predicts as the only site where we do get that very low nitrate concentration right up high at that intermediate, almost upper ecogeomorphic zone location. So that's the framework for research question number 2. And now we have all the tools to answer. How does delta morphology influence nitrate removal capacity in river-dominated deltas? So I've already demonstrated that in Waxer Delta that the modeling approach works pretty well. And now I use 6 synthetic deltas, again developed by collaborators. And these were all created using computer modeling software, Delft 3D to be specific. So we have a little bit of a different orientation to Waxer Delta. Here we have flow from south to north. And we've, let me explain the models a little bit. These 6 deltas were all formed using the exact same parameters in Delft 3D, except for grain size distribution represented here by this D50 here. And what we see is if you just change grain size, you can have deltas with very different morphologies being formed. So if you apply reactive transport on top of that now, what we see in here, the first thing that comes to mind is that you can see is that it's all that deep red color for the most part. We're not really getting that much removal in all of these deltas. The white areas represent the sub-area locations. You are seeing areas where you do get full nitrate removal in locations near the sub-aerial parts. But for the most part, you are we're not getting too much removal. And so I have here 3 end members, one representing silt, another verifying sand, and another coarse sand. And I'm looking here at the optic length, which is a different name for spiraling length. They're pretty analogous. And again, back to this optic length or spiraling length. What is it? It's essentially the distance a molecule will travel. In this case, we're talking about nitrate. So let's just stick with nitrate. So the distance a molecule of nitrate will travel in the water column before it is removed out of the column, due to, again, a combination between the biotic processing rate as well as the transport. So I have here highlighted in these 3 deltas optic lengths that are less than 4 kilometers, represented by this light blue color here. And that is important because that is the general length scale of the synthetic model. So an optic length less than 4 kilometers would suggest that the nitrate is being removed from the water column before it escapes out of the delta past the delta front out into the basin. Now we could look at more of a cross section of the delta. I have here highlighted in blue the delta islands. The black represents the delta front and the delta basin. And we see different shapes of how the delta sits up relative to sea level. So this silt delta we have, it's pretty much flat, and we get a removal of about 2.5%. In this very fine sand delta, we have a delta that sits up a little bit, and we have a removal of about 4.7%. And finally, we have a removal of about 6.7%. This is the most that we saw in all of our synthetic deltas on the delta that sits up the highest. So we could put all 6 deltas together, and what we see here is a nice regression between delta slope and nitrate removal. And how I explain this is, in real life, if these were real deltas, the ones that set up a little bit more, those are the areas that are able to form, those are the deltas that are able to form these wetlands that process more nitrate. What is interesting, and I didn't expect this, is we saw in our 6 deltas a decrease in nitrate removal with delta area. And this is not to say that the smaller the delta, the more nitrate removal. What it's saying is that the delta area may not necessarily mean, the bigger the delta may not necessarily mean that you're going to get more removal, because you can have a very big flat delta, as could be seen here in the silt delta, that is below mean sea level for the most part, and you don't really get those wetlands being formed. You don't really get that high process, those hotspots. Or you can have a smaller delta that sits up a little bit higher, that has all the wetlands and the hotspots that can process nitrate a little bit faster or more efficiently. And I have here, to wrap up, some implications for wetland reclamation. We know here that in the Gulf of Mexico, we have most of it are projected to lose land. There are only a few areas in green here where you get growth of land. And if there have been studies or aims, desires to increase the amount of land, or at least halt land loss. But if the goal is to increase the land so that we can increase the nitrate removal efficiency, then I would suggest that, at least the study suggesting, is that we would probably want to divert sediment that have larger grain sizes. So we see here that as increased grain size, we get an increase in nitrate removal, and that's because at increased grain size, you get those deltas that sit up a little bit more compared to finer grain sediment, where the deltas lie a little bit flatter. So to summarize again, back to the key points, I hope I showed you that higher elevation ecogeomorphic regions contribute most to nitrate removal. And I hope I showed you again that high sitting deltas are more efficient at nitrate removal than lower deltas. And we saw together that nitrate retention is likely limited to only a few percent. In none of our simulations, we saw more than 7% nitrate removal. So I'm going to transition here into our Great Lakes study. So we're moving from Waxahachie Delta and the Atchafalaya into the Great Lakes. And again, we're going to go through the key points up front, and then we'll work through the methods and the results together. All right, back at the key points. So I'm going to show you for this part that groundwater delivers a small yet substantial amount of nutrients to the coast of the Great Lakes. And we're going to see that 43% of the US Great Lakes coast is vulnerable to groundwater-borne nutrients. So again, we have, this is a beach on Lake Erie, and we'll be considering direct groundwater discharge. So for those of you who are unfamiliar, it is essentially groundwater that discharges directly to the coast or on offshore without being intercepted by some river. And again, it is diffuse. It happens across the entire coastline, but it is, in this picture, I'm sure it's happening, but we can't really see it, and it's very difficult to measure. So we estimated direct groundwater discharge using a water budget approach. Now, if you consider a catchment area any water that enters this catchment area is going to be intercepted by a river before it discharges to the coast by definition. You can have the areas in between these catchment areas called coastal catchment areas, where any water that intercepts this area is it's not going to intercept any river, but it's going to discharge directly to the coast before being intercepted. And if you make a couple of assumptions that whatever comes in must go out, so recharge equal discharge, and we assume that the water extraction is negligible, and we assume that regional flow is negligible, we could come up with an estimate of direct groundwater discharge. So we used the National Hydrography data set to get the coastal catchment area and the North American Land Assimilation System model to get an estimate of recharge within those catchment areas. And we're able to come up with an estimate for direct groundwater discharge based off of, again, recharge and the area of the coastal catchment. And putting all of this together, we are able to come up with a map of direct groundwater discharge of the Great Lakes. And what you might see here immediately is that whereas Canada, and nothing against Canada, it's just that the NHD data set that we use is not available for Canada, so we were limited to the US shoreline. Although there's analogous data sets for Canada, the resolution is not quite the same, and we made the call that it's probably better to compare apples to apples and just leave that alone for now. So we're only looking at the US Great Lakes shoreline here. And the other thing that you might see is that the direct groundwater discharge is very variable. What you can't see immediately from this map, but thankfully I calculated it already, is that Lake Erie has the highest rate of direct groundwater discharge, and Lake Ontario has the lowest rate. We have the total discharge is about 2.54 kilometer cube per year. But what about the nutrients? We know that urban areas and agricultural areas tend to be tend to have high groundwater-borne contamination. So what I did was say, hey, if the direct groundwater discharge is high, and it also intercepts land use that is either urban or agricultural, I'm going to call this vulnerable to groundwater borne nutrients. So you put that together, and what we get is 15% of the US Great Lakes shoreline is vulnerable. We see here that Lake Superior is the least vulnerable. I think it's less than 1% of that shoreline is, and Lake Erie has the most vulnerable shoreline. And again, I want to stop here to point out that, hey, I'm not saying, Deon isn't saying, oh, hey, look, 15% of the US is definitely vulnerable. There's definitely contamination all along this pink area. No. What I'm saying here is, if you were to make a best guess of areas that could have groundwater contamination, areas that are vulnerable, that 15% is where I would look, those pink areas. That's where I would look to find some sort of direct groundwater discharge related vulnerability or contamination. And this was a nice, remote sensing pretty much map model, but we did some ground testing as well. So we chose a vulnerable site on Lake Erie, partly due to convenience, close to home, Columbus, Ohio at that time. And we did a seepage meter study, and again, that's another big word for essentially, again, a 55-gallon drum, this time with a plastic bag attached to it. So you stick the seepage meter into the sediment water interface, and you have the bag attached to it. And if there's seepage, you can measure the mass of water that enters the bag with time, and you get your seepage rate that way. So we did, so we had 3 shore perpendicular transects, and we had 1 shore parallel transect. And what we see is that we got about 354 meter squared per year at our study site. That's what we measured. The water budget approach indicated that at this location, it would have been 588 meters squared per year. So our water budget over predicted a little bit, what we saw, but we felt pretty comfortable with this number, considering the huge variability that we observed for all of the Lake Erie. And we have several explanations of why we measured a little bit lower than the water budget. The main reason that we think is right here, just right onshore here, there's a little wetland, a little lagoon that likely intercepted a lot of that direct groundwater discharge before it could have be discharged out offshore. But again, back to the nutrients. So we measured dissolved inorganic nitrogen and dissolved phosphorus in the seepage meters, well, at the seepage meters and on some onshore wells. The darker color means greater concentration. And what we see in here with the dissolved inorganic nitrogen is that we have high DIN in the onshore wells, but relatively low DIN in the offshore seepage meters. So this is saying that we're probably getting some sort of removal happening right even in that little shallow near flow path between the groundwater, between the onshore wells and the offshore seepage meter. We see a little bit of the opposite with the dissolved phosphorus. We have low on onshore wells, but we see a higher concentration offshore. And this is probably representing some sort of mobilization of phosphorus in the lake bed sediment that we're picking up on the offshore seepage meter that is not found in the onshore wells. So what is the relevance? What I did was extrapolate our findings. So I extrapolated our concentration findings, and I used the water budget approach for all of the Lake Erie. And I said, if you do concentration times flux, what would be the flux of nutrients to Lake Erie from direct groundwater discharge only? And what we see is we got 5.43 grams per second of dissolved inorganic nitrogen. And that represents about 4% of the annual load of the Maumee River. So the Maumee River is one of the major culprits of nutrients into Lake Erie. So one of the bigger contributors. And with direct groundwater discharge, we get about 4%. So not a whole lot, but not nothing. Same here with phosphorus, we get 2.5 grams per second of phosphorus from direct groundwater discharge, and that represents about 30% of the annual load from the Maumee River. So what is interesting is we get in flux from direct groundwater discharge that is a little bit different in the chemistry of surface water. In the surface water, we have a high nitrogen to phosphorus ratio of 147 to 1. So a lot of nitrogen coming in the surface water, coming into the groundwater, and you could compare that to about 21 to 1 coming in the surface water. So this tends to contribute to the direct groundwater discharge tends to contribute more to phosphorus limitation. So again, back to our key points again, I hope I showed you that groundwater delivers a small yet substantial amount of nutrients to the coast. And we see here that 43% of the US Great Lakes coast is vulnerable to groundwater-borne nutrients. I'd like to take a second or two to do my acknowledgements.
Well, great. Thank you very much for the informative presentation. That was really nice.
Yeah, thank you again. Thanks for having me. I had a lot of fun.
Yeah, Yeah, thank you. Thanks for coming, and thanks everyone for joining us. Goodbye. I'm going to end the meeting now.
Okay.
Yeah.